Look up at the night sky. You're seeing a tiny fraction of existence. It contains every star, planet, and particle spinning inside every single atom. Yet everything we have ever observed, touched, or measured makes up barely 5% of that reality. The rest is a massive, invisible void of matter and energy that we cannot directly detect. To understand what is hiding in that missing 95%, we have to trace the universe back to its very first moment, before galaxies, before atoms, and before time itself. 13.8 billion years ago, there was no empty space. Everything that would ever exist was compressed into a singularity, a single point of infinite density and unimaginable heat. Then came the Big Bang. Space itself expanded from that central point, stretching in all directions at once and creating volume where there was none. In the first trillionth of a second, the universe inflated faster than the speed of light. That violent, instantaneous stretching locked in the physical laws that dictate both the planets we walk on and the cosmic forces we cannot see. At the 3-minute mark, the expanding space cooled enough for basic particles to stick together. Protons and neutrons fused, creating the first atomic nuclei: hydrogen, helium, and a trace of lithium. But the universe remained dark. For the next 380,000 years, space was an opaque, blazing hot fog of ionized gas. The plasma was so dense that light could not travel a millimeter without crashing into an electron. Eventually, the universe cooled enough for those free electrons to bind to nuclei, forming the first neutral atoms. The dense fog finally cleared, and light could travel freely across the vacuum of space. That specific flash of first light is still traveling today. We detect it as the cosmic microwave background radiation, a faint static washing over us from every direction, providing a record of the infant cosmos. As the universe matured, an invisible scaffolding took control. Dark matter makes up 27% of the cosmos. It does not emit or reflect light, but its gravitational pull is the only thing keeping rapidly spinning galaxies from tearing themselves to pieces. Then there is the remaining 68%, dark energy. While dark matter acts as a cosmic glue, dark energy is a repulsive force embedded in the vacuum of space itself, actively accelerating the expansion between galaxies. These opposing forces govern the large-scale distribution of matter. Dark matter pulls mass into clustered structures, while dark energy stretches the empty space between them. Tucked inside those galaxy clusters are stars. A star exists in a state of balance, where the inward crushing force of gravity is perfectly offset by the outward pressure of nuclear fusion in its core. When the most massive of these stars run out of fuel, they collapse and detonate in supernovas. The remnants left behind can become black holes, regions where gravity becomes so extreme that standard physics breaks down. Zoom out, and the scattered lights resolve into an interconnected network. Stars gather into galaxies, galaxies bind into massive clusters, and those clusters string together to form the cosmic web, vast filaments of light separated by enormous voids of absolute darkness. Within these glowing threads, stars operate as localized factories. They spend billions of years fusing simple hydrogen into the heavy, complex elements required to build rocky planets and biological life. As dark energy continues to stretch the universe, cosmologists project a few possible endings. The first is the Big Freeze. The universe expands until stars burn out, the gas necessary for new ones is depleted, and everything reaches a state of absolute freezing stillness. Alternatively, if dark energy accelerates further, we face the Big Rip. The expansion of space becomes so powerful that it physically shreds galaxies, dissolves planets, and eventually tears apart the atoms themselves. The final scenario is the Big Crunch. If the combined gravity of all matter eventually overpowers dark energy, the expansion stops and reverses. The entire cosmic web falls back in on itself, crushing reality back into a single point. We do not yet know which of these endings is coming, but knowing that the universe will eventually expire means our current era, a time filled with burning stars, liquid water, and complex structures, is a strictly limited window in the cosmic timeline. That limited window allows for something remarkable. The iron in your blood, the calcium in your bones, and the carbon in your cells were physically forged inside the cores of ancient stars and scattered across space to eventually form the Earth. Now, those scattered elements have organized into a species capable of looking back. We build tools, like the James Webb Space Telescope, to capture ancient light and study the universe as it appeared when it was just an infant. You are made of stardust. We are the physical result of these cosmic cycles, now looking back to map the processes that created us. With 99% of the cosmos still unmapped, most of the landscape remains to be discovered.